We're going to quickly run through a few examples here. It says see circle A, and we're going to draw the following. First of all, we're going to draw a line that is tangent to circle A at point C. So here's point C, and I remember that a tangent is a line that touches the circle in one point but does not pass through that circle. So if I could draw a little bit of a straighter line there, you would see that this is a straight line that touches that circle at point C. And point C here is called our point of tangency. So we're going to learn a little bit more about that later on, but this is a point of tangency. A radius AB, well, that's an easy one. We're just going to connect this line segment here, AB. Chord CD, remember a chord has its two endpoints. The line segment has its two endpoints on the circle. A secant, BD. Secant is a line that passes through a circle. And there you have, there's our line BD. It keeps going off in both directions and it passes through that circle. A diameter ED. Diameter passes through the center. It's a line segment. Passes through the center and has its endpoints on the circle as well. So an interesting thing about a diameter is also a chord because it fits the definition for a chord. And that's simply that it has its two endpoints on the circle. A point R that lies on the interior of the circle. Here's a good point for R. Point S that has its exterior. There's point S. A circle Z that is tangent to circle A at point E. So if it's tangent to circle A at point E, let's just say here's our circle Z. Circle W that is tangent to line L. Here was line L, remember? And if we wanted a circle that is tangent to it, we can draw any kind of circle here, but we'll just draw a small circle right here. And we'll call that circle W. And then finally a concentric circle X that lies inside circle W. Well, you can see here that I've drawn way too small a circle, but there's two concentric circles. Now we're going to take a look at a few theorems about circles. This first theorem, we're going to explore a tangent. A line that is tangent to a circle is always going to intersect that radius of that circle at a 90-degree angle. So you can see over here that as I drag point B around the circle, that this line, that CB, is tangent to the circle at point B. It's always going to intersect it at 90 degrees. So one of the things that I can conclude about this theorem is that this line AB and the tangent L are always going to be perpendicular. So radius AB is going to be perpendicular to line L because it's tangent. The next one we're going to take a look at is its converse. So conversely, if a line is perpendicular to a radius of a circle at a point on the circle, then the circle must be tangent. Then the line must be tangent to the circle. Therefore, if I know this is a 90-degree angle, then I also know that this line L is tangent to that circle, and therefore, is tangent to the circle and is perpendicular to that radius AB. Now we're going to take a look at this last theorem here. And the last theorem says if two segments are tangent to the circle from the same external point, then the segments are congruent to each other. Let's take a look at what that situation might look like. Maybe. There we go. I'm just going to swing this over here and I'm going to drag my point outside the circle. So here is line segments DE and DF. They are both tangent to the circle from the same point D. And what you'll notice is that the line segments are congruent to each other. No matter where I drag them, as long as they're tangent to the same circle from the same point, they are always going to be congruent to each other. So my conclusion is, in this picture, that line segment EF must be congruent to line segment EG because they're tangent to the same circle from the same external point. Let's try a few of our examples. It says AB and BC are both tangent to circle O from the same point. Find the value of X and find the length of BC. Well, I just learned that these two segments must be congruent to each other. When two things are congruent, I can set them equal to each other and I can solve for the variable. In this particular case, I need to first distribute the 2 to inside the parentheses here. So I'm going to simplify the side to 6x minus 14. This is set equal to 4x plus 8. Now I need to combine my like terms. When I do that, I'm going to move the 4x over here by subtraction. That leaves me with 2x. And I'm going to get the negative 14 over here by the inverse operation of subtraction, which is addition. So that leaves me with 8 plus 14, which is 22. Divide both sides by 2 now. X must be equal to 11. Once I found the value of x, I can go back and I can find the length of each one of those segments, which in the end, they should be the same. Let's take a look at example 3. It says find the radius of both circles. Well, for circle S, I'm just going to count my spaces to the border. That's 1, 2, so my radius here of circle S must be 2. My radius here for circle R looks like it's going to be 2 as well. That's funny because they look like different size circles. Let's try counting that again. 1, 2. Yep. 1, 2. They look the same. Okay, the point of tangency, remember, is the point in which they touch. So the point in which they touch here is this coordinate. -1, -2. -2 over and 0 up. That's 0. Finally, the equation of the line of tangency. Well, the line of tangency is going to be the line that touches both of those circles at that same point, or that point of tangency. In this case, it is a horizontal line that goes left to right, and it's the x-axis. So this is the case when y equals 0. Now, just as a general reminder, the equation for a horizontal line is always going to be in the form of y equals, and it's going to be whatever that y coordinate is of that point of tangency. Okay, so it's the y coordinate of the point of tangency. Likewise, the general equation for a vertical line takes on the form of x equals, and it's always the x coordinate. Our final example, we're going to take a look at this story problem. It says the surface of the Earth is approximately 4,000 miles from the center. If a satellite orbits Earth at 120 miles above the surface, find the distance from the satellite to the horizon. Well, here's kind of a cross-section of our Earth. Here's the center of our Earth. It's 4,000 miles to get to the surface, plus an extra 120 miles. Here at H is my satellite. So my satellite rests actually 4,120 miles from the center of the Earth. Now, the distance from F to G, again, is just the radius of this cross-section of the Earth. So it's also 4,000 miles. If I want to find the distance from the satellite to the horizon of the Earth, that's from H to G. Here's my horizon, right? If I look off here, I can see the satellite just over the horizon. Well, this distance here is really just a leg of my right triangle that I created. Because remember, HG is tangent to this radius. So I've created a right triangle in which I know 2 out of the 3 sides of it. And whenever I have 2 out of the 3 sides, I can find the third side using Pythagorean theorem. So I'm going to set up my Pythagorean theorem that says 4,000 squared plus x squared is equal to 4,120 squared. Because remember, this 4,120 is my hypotenuse. Now, I got to check out my notes here. I'm going to subtract my 4,000 squared from both sides. And remember, I'm going to square them first. So I can't say that this is equal to 120 squared. I actually have to square them and then do the subtraction. When I do that, I will get 974,400. So 974,400. And now I need to take the square root of both sides. And when I do that, I'm going to get approximately 987.1 miles. So the distance from the satellite to the horizon is 987 miles.